Okay, so my name is Toby Cambray. I'm from Greengage Building Energy Consultants. That's a consultancy practice that I founded 6.5 years ago. And we do a variety of things, including Passivhaus, consultancy and design. We also do mechanical, electrical design, and a lot of other building physics type stuff. So hydrothermal modelling, IES and TAS. But we really like Passivhaus, and hopefully I'm going to persuade you that it's a good idea too. Has everyone heard of Passivhaus before? Yeah? Has anyone looked into it in any more detail? Yeah? One. Okay. Fine. So the structure of the talk today is basically I'm going to go through an introduction to Passivhaus and talk about the standard and the way it's structured, and some of the benefits. And then I'm going to go through a case study of projects actually quite unusual even in the context of Passivhaus. So hopefully if you have been looking into it, then this will be something a bit different there. But you just bear that in mind that it's not a house, and it's a retrofit project. So it's kind of unusual in those two respects. One thing to probably just clear up at the start here, if we've got any German speakers in the audience, you'll know that house is the word for building, not for house in English. So yeah, obviously the passive bit means it requires, in theory, less heating, or is taking advantage of solar and internal gains, and then the house bit is the building. So it's not just houses. Let's see if I can make this work. So this is a slightly sort of geeky technical definition of what a passivhaus is. So a passivhaus is a building in which thermal comfort can be provided solely by heating or cooling the fresh air inflow which is required for good indoor air quality. So that's basically without any air recirculation. And in that is kind of bound up all of the theory. So it's quite a simple sentence, but when you start to unpack that, it's quite a lot more. There's quite a lot more to it. So in practice, we're basically talking about a building with very low space heating demand. There's got very high thermal comfort in there, and we achieve that basically by focusing on very high levels of fabric performance, and then putting some sort of minimal heating and ventilation systems into that afterwards to provide that sort of residual demand. It's also important to look at the building in the whole context. So we look at the energy used by heating hot water, lighting and appliances, and there's some really good research that backs all this stuff up to show that it actually works. So one of the key things that Passivhaus does is it closes the performance gap that I'm sure you've heard about, and we'll go on and talk about that a bit more. Passivhaus sometimes gets a lot of stick about resulting kind of boring buildings, but it's independent of aesthetics, and we're involved with some quite architecturally exciting things, and that does have implications, and we'll go on to that in a bit more detail in a minute. But it's essentially it's a descriptive standard. It's not a prescriptive standard. So that means we're saying you've got to hit a certain energy target. We don't care how you get there, and here's a tool for calculating that. But ultimately, the design's got ultimate flexibility about how they achieve that. So these are the key criteria. So to achieve Passivhaus. So they're split into two categories really, and there is a lot of crossover between these things. So the Passivhaus is as much about comfort as it is about energy. So we could make a very low energy building, by just like having a tent and like not having any heating or whatever, and that would be low energy in the sense that we're not putting very much energy in, but it wouldn't be very comfortable. So what we're doing here is we're saying let's aim for a really high standard of comfort, and actually higher than you'd get from a typical sort of UK regulation house or building, and then do that in a way that's really low energy. So the comfort's really, really important as well. So we're talking about very low levels of air tightness, or very good air tightness rather. So that's measured in this case, air changes at 50 pascals. So that's the blower door test, where you put a big fan in the door and you pressurise the building up to 50 pascals and measure how much air is flowing through that fan, and that tells you how leaky the building is. So that's about 10 times tighter, roughly, than a typical UK house that's being put up at the moment. So very airtight. Internal surface temperatures must be above 17 degrees Celsius at all times. And the key implication of that is that in the UK, we're pretty much obliged to have triple glazing. And notice that this is in the comfort criteria, not an energy criteria. So although triple glazing is going to save us a significant amount of energy, it's also really important to have that in there to keep our internal surface temperatures up, so that because we perceive temperature as a function of radiant heat as well as air temperature. So by raising the internal surface temperatures, by having better insulated glass, which is generally the weakest point, we're increasing the thermal comfort. Summer overtime heating is fairly self-explanatory. That needs to be below 25 degrees, or can be allowed up to over 25 degrees 10% of the time. There's a whole other discussion, and that's not necessarily a perfect criterion. There's other ways that you can measure that might be better, but it's not too bad. The ventilation rate is 30 meters cubed an hour per person. That's about 8 or 10 litres, or 12 even litres a second per person. And then the energy demand is 15 kilowatt hours per square metre per year, assuming we're heating to 20 degrees, or 10 watts per metre square heating load. And the latter thing there, the 10 watts per square metre, that is basically the heating load that you would need to hit in order to be able to do the thing in the first sentence up here, to heat the building solely by providing uncirculated fresh air, on the basis that you don't want to heat it too hot for thermal comfort purposes, and you're only allowed, you don't want to over ventilate the building, because then you tend to dry it out. And if you crunch those numbers, then you get to about 10 watts per square metre. And as a primary energy demand, which is kind of the closest thing that we get to CO2 measurement in Passivhaus, but it's expressed in primary energy, so that's kind of the energy that we dig out of the ground. There's also Passivhaus Plus and Passivhaus Premium now, which are basically the Passivhaus Institute's response to the European nearly zero energy building thing, and that basically is the fabric bit is all the same, but it will take into account the renewable energy to try and bring this 120 closer to zero. The Passivhaus standard is often referred to as a fabric-first approach. So we're really interested in how the fabric of the building performs, like I said, and not so much to do with the systems, although that's important, but the first thing is to get the fabric right. So we're talking about having no drafts, no condensation or mould. Again, that's a surface temperature thing, really. Radiant discomfort we talked about briefly, some overheating, lots of fresh air, the right amount, so we're getting plenty of fresh air, but not so much as to dry the building out. And I don't know what that phrase means, whole house warm, anyway. And obviously, so fuel poverty is a big topic nowadays as well, and we're involved with quite a large number of social housing. So I think we've got about almost 150 social housing units on the books at the moment that we're working on. So it's a popular thing in that sector. This is some more of the kind of the theory. So there's a tool called the Passivhaus planning package, which goes is part of the Passivhaus methodology, and it's fairly simple. It's basically a very big spreadsheet, and it works on the degree day principle. So it's not a dynamic tool, but the research that's been done shows that certainly for houses and a lot of other buildings, it doesn't matter actually. That's okay. As long as we fill in our spreadsheet really accurately, then that's more important than having some really sophisticated tool. It's also, and so the spreadsheet's been calibrated kind of against both dynamic simulation and real world measurements. So it's not just sat there in sort of theoretical isolation. And this just summarizes sort of the three categories of conductive heat loss that spreadsheet accounts for. So you've got your U values times your areas, your linear heat, linear thermal bridges, and point thermal bridges sometimes as well. So we're interested in all of those really, and wherever possible, we're going to design these out, these thermal bridging factors. So when we're doing that is this general strategy. It is just a general strategy, it's not always possible. So yeah, we have an uninterrupted layer of insulation, the structural zone separated from that, surface zone on the inside, and then the red line there is a really important one, so that's your airtightness layer. That's the thing that's going to give us that 0.6 changes per hour. Obviously, when you actually come to draw this in a real detail, then it gets a lot more complicated. But that's kind of what we're aspiring to. So going back to the airtightness for a moment again, one way that we can express this is for a building regulation standard house, you can get away with basically a hole that's the size of 5 20p pieces in 5 square meters of wall. So probably something a bit smaller than this screen here. You'd be allowed to have 5 20p's worth of hole in that screen. For Passivhaus, you're allowed 1 5p. So it's a slightly weird way of expressing it, but very small leakage area. And yeah, when we get to the case study, we'll talk a bit more about how we do that in practice. So this is a little bit about servicing a Passivhaus. It's not a terribly good diagram actually, but again, for thermal comfort reasons, it's quite important to have an MVHR unit, so mechanical ventilation with heat recovery. So that basically means that we can supply fresh air in at over 16 degrees, which is important for thermal comfort, but we can do that without having to heat the air artificially, because we're just recovering the heat from the stale air on its way out. This system has is showing a preheater so that we can avoid frosting up the coil. So a lot of MVHR units, certainly on the market in the UK, if they get frost on the heat exchanger, they have to shut down the air supply, and one way or another you get less supply air in when it's really cold, and we don't like that because we want lots of fresh air. So yeah, we have to sometimes do a bit of preheating of the air, and you can do this post-heating thing as well, but yeah, it turns out that's not such a great way of doing it. Anyway, moving on. So this graph is one of the sort of outputs that you can expect from PHPP, and we use this a lot in our practice to just kind of get a feel of the direction of travel of the design, and you can infer a lot of things from this graph that will help you refine the design further. So you can see on this one, for example, our heat losses. So to explain it a bit more, we've got on the left-hand column is a breakdown of all the heat going out of the building, and the right-hand column's all the heat that's being added back in to maintain that 20 degrees. So you can see the solar gain is a significant proportion there, and we've got the green part of that column on the right is internal gains. That's body heat, cooking, gains from lighting and stuff like that, and then the red bit's just stuff that we have to add through the heating system, so kind of artificial heat, as it were. And then on the left, we've got a breakdown of all the heat losses. So on this particular project, there's quite a lot through the walls and quite a lot through the windows. But we can see we've reduced the heat losses through ventilation down by using our MVHR. The infiltration losses, that's the air leakage from the building. They're pretty small as well. There's a little bit left in there for thermal bridging. And the walls and the floor and the roof are pretty good. So that's a fairly typical kind of graph. And you can see our 12.6 on there is below our 15, so that's all good. So we talked about how Passivhaus is independent of aesthetics. In reality, obviously, it's all physics really. So yeah, it does have an impact on the design of the building and therefore the aesthetics. So the shape of the building is really important, and actually it's one of the biggest factors that a lot of people don't necessarily grasp straight away. If you've got a nice compact form, that by which we mean you've got not very much surface area compared to the available floor area, then a more compact form is good because we've got less area to lose heat through. So less area means you don't need to have quite such stringent U values. So this building would be an example of one that's quite a good compact form factor. We've got quite a lot of floor area. There's not too many kind of wiggly bits and things sticking out that are kind of that are kind of expensive in terms of floor area to wall area ratio. The glazing, we want to be optimizing our solar gains to some extent, but the experience from the Passivhaus community is that you don't want to go chasing those solar gains too hard because you basically end up with summertime overheating, and yeah, that's a really big issue nowadays. That the building regulations, certainly for domestic stuff in the UK, aren't addressing well enough, and we're building up a lot of issues that are going to come back to bite us pretty soon. So Passivhaus is definitely not the same as the passive solar houses from the 70s. So when we had the first sort of oil crises, people started looking at how we can reduce energy demand from buildings. One of the ideas was to have acres of south-facing glass to catch all that solar heat. And while that kind of, yeah, that does work in that sense, and it catches a lot of solar heat, it means that you just get really far too hot in the summer and you have to have air conditioning, and that's a bit of a self-defeating thing. Air tightness, yeah, we talked about. So you basically need to have one continuous air barrier all the way around the building. So if you take any section or any plan, you should be able to put your pen on the paper on the air barrier and draw a continuous line around it and link all that up. So that's an important exercise that we typically go through during the design process. The insulation is pretty thick on the whole, certainly thicker than typical kind of regulations house. Although the building regulations are kind of catching up on U values actually, they're not that far away. So yeah, that's kind of an interesting thing, and a lot of people go to quite thick levels of insulation on sort of non-Passivhaus buildings, but it's a whole package. So you can't just have thick insulation and hope that you're going to get the kind of levels of energy performance that we're talking about here. One of the things that's really important is to make sure that it's thick and thermal bridge free. So that's kind of one of my other bugbears that I'll avoid talking about too much right now. But thermal bridging is really important, and make sure it doesn't happen. Ventilation, yeah, we've got heat recovery on and it's in a mechanically ventilated. So the mechanical ventilation allows us to have a nice consistent level of fresh air. So obviously with natural ventilation you're dependent on wind and stack pressures, which are somewhat variable. so the mechanical ventilation kind of avoids that, and it means that we get always get the right amount of fresh air. So that the small amount of energy we need to turn the fans is, on a properly designed system, is more than offset by the energy that it saves. This is some technical stuff about how we define heat loss through a window, and I won't go into too much detail here, but it's a lot more comprehensive in the Passivhaus planning package than it is in the SAP calculation, and actually even in things like IES and TAS, in my experience. You can build this sort of information into IES and TAS, but it's quite hard work. Anyway, and our window U value has to be below 0.85 in order to get that internal surface temperature of above 17 degrees. So this is one of the key outputs from a bit of research that underpins the whole Passivhaus thing. And as you'd expect, we've got a fairly broad range actually of total energy usage, down from sort of 3 or so kilowatt hours here for some weird buildings, up to getting on for double the target actually, so over 25 kilowatt hours per square meter. But the average is coming out pretty close to actually slightly below the target of 15 kilowatt hours per square meter per year. So what that's saying is that Passivhaus over this 53 projects we got here, the performance gap has been closed. And the other aspect that we haven't really talked about much yet, I'll touch on briefly because I'm about to move on to the case study, is the QA element of Passivhaus. So that's basically paperwork, but it means that's, to my mind, that's the key thing that allows us to really close that performance gap down. One of the things that's kind of missing out of the regulations at the moment. So typically on a Passivhaus project, you have a Passivhaus designer, so someone like me that's involved in the design team and getting involved in detailing the thing up. You're also obliged to have, you don't need someone like me, by the way. If the architect is Passivhaus certified and they're competent, then that's fine. But what you must have is an independent, qualified, third-party Passivhaus certifier. And they basically QA all of the calculations and all of the design work that we do to say, yeah, that's a Passivhaus. And that bit of the process is completely missing from building regulations at the moment. Well, I say it's completely missing. In theory, building control should kind of have some role in that, but it's nowhere near as thorough as the kind of QA that you'd get out of Passivhaus, of going through the whole process. So, what was I going to say? Yeah, so the key thing is that we come up with this design, and we can do loads of calculations on the design to make sure that that's going to be up to standard. But then we've got to make sure that our design matches the calculations. So there's a bit of QA to do there, and then we've got to make sure that what gets built matches the design, and only then do we have a complete chain from building to back to calculation. So that bit's is really important. So this is a youth hostel, which we were involved with the design of, which is up in Cirencester, so not too far from here. It started life a very long time ago as a warehouse associated with the brewery, which is in the building just on the right-hand edge of the picture there. And it's called the Barrel Store, so that's that. It's basically an old stone barn, very thick Cotswold limestone walls, 500 millimeters typically. We were approached to convert that into a youth hostel a few years back, and that was completed middle of last year. So this is what it looked like originally. It's been cleaned as part of the work. It's part of the Brewery Arts Centre, which is a sort of arts organisation in Cirencester. And one of the reasons they wanted a youth hostel was to provide accommodation for their residential courses. But you can go and stay there as a member of the public if you've got your YHA card, or even if not, I think. But anyway, this is the back of the building on the left-hand side here. So it faces onto a pub and some other properties. And it had been converted in the early 80s into a theatre. So that's a picture looking up from the stage effectively up into the roof. This gives you a little bit of a better idea. So this is the state of the building when we got hold of it. Yeah, it basically fallen out of use as a theatre and was no longer sort of fit for purpose. There's another theatre in Cirencester. So yeah, they came up with a plan to convert it into a youth hostel. And this is the scheme that we ended up with. There's the ground floor, so we've got an entrance lobby, communal sort of kitchen area that can be used as a meeting room as well. These are bedrooms and ensuite bathrooms. So each bedroom, apart from the accessible one, I think has, they mostly have 4 beds in there over two bunks. So that's the first floor. We've got this rather nice curved staircase coming out there as well. And the arrangement's designed so that, for example, this door can be locked separately, and then a family or whatever can have this sort of suite of 2 rooms, for example. So there's some sort of flexibility designed into the layout from a practical point of view. And then we've got some plant space on the second floor. It's not as big as it looks because that's the section. So this space down at the bottom here was actually a sort of void space. So there's a long step down from outside to inside. You might be able to see that in the photos. Yeah. In order to make this all accessible, we looked at various options to try and get 3 floors in because of the extra space we had there, and it was very difficult to make that work. So we basically filled that space up with mostly insulation. Didn't need to be, but it had to be filled with something. There's another section through the staircase, and you can see we've effectively internally insulated the walls, and the windows are placed in the plane of the insulation to minimise the thermal bridging at that point. There's some elevations. So some of these openings were existing, some of them were moved or adapted slightly, and a couple of them are brand new. So this was the front entrance here. We retained the circular window, which was, I'll come back to that one. Yeah, that's the back of the building and the sides. So not very much window space actually. We've got there's a roof light over the stairwell to get some natural light down there, but all of the bedrooms have a window, so they all have the ability for natural ventilation apart from the one with the circular window, because we can get one that was opening as well, and that's probably one of the faults with the project actually. So if you go there, don't get that room with the circular window. These are some of the details. So this is getting into how actually achieved standards. So this is a typical wall build-up, and you might be aware that insulating solid walls is not trivial. Existing old solid walls, in particular, due to the moisture behaviour, the way moisture moves around in those walls. Because when we add insulation, particularly internally, we change the way that both heat and moisture flow through that wall. What we came up with is a solution that's largely wood fibre. So we've got 2 slightly different kinds of wood fibre insulation. This one is a rigid board that's bonded onto the existing stone wall with a lime-based product, and there's a more flexible mineral wood wall type product between the timber frame. So basically, on this detail, you can see this a bit more clearly. So this is a section through the ground floor detail. We filled up that zone with quite a lot of insulation and some other stuff below that. And then we have a structural concrete slab that was cast on top of that with a bit of insulation around the edge to reduce the thermal bridge there. And then there's basically a new timber frame just built off of that concrete slab. So that's kind of how it's working structurally. We've got something that's completely independent, really, of the existing stone structure. Yeah, you can again see the
even your internal floor doesn't go to the original wall?
Yeah. So on the right-hand side here, that's the detail of that internal floor. It just spans out onto the timber frame here.
Where your one is, that's actually a solid wall? Yeah.
Correct, yeah.
But everything within the building?
Yeah. Yeah, and it got a bit more complicated up at the roof because we've got those existing trusses. But yeah, essentially...
How thick altogether? Metre?
So it's 500 of stone. I think it was 80 or 90 of that layer of insulation. That's a 90mm stud. So it wasn't a whole metre. It was most of a metre. And this achieved a U value of, I think it was just below 0.2, which is relatively high for a Passivhaus, but with the refurbishment version of Passivhaus, the criteria is slightly relaxed because it's really hard to do. So we're aiming for 25 kilowatts per square metre per year rather than 15, so we can get away with slightly higher U values. But they're still pretty good, even by new build standards, kind of. The roof was an interesting challenge. So that when they converted it into a theatre, they put a bit of insulation between the rafters, but it was nowhere near enough what we needed. A design stage, it was decided it was too expensive to remove that. So we actually came up with a solution where we put new insulation below that and had a ventilated void beneath the original insulation that's not original, which was not a great solution, and in the end they took the roof off anyway, and only told me afterwards that they'd taken the roof off, and in which case we could have taken the old insulation out and done something that was much more satisfactory, but that's what happens on construction projects. That's the detail just where an internal wall meets the external wall in plan. So again, everything's within that timber frame structure. There's a couple of points. The structural engineer wanted us to have a couple of straps. The walls were starting to belly out a little bit, so we've got, I think it's 2 structural straps that are trying to pull that belly back in, and they are linked up with a thermally broken structural tie where it penetrates the insulation there. How are we doing for time? 10 minutes. That's a roof light, and it's a roof light installation. So again, we've tried to tie up the insulation with the roof light because at that point that's what's doing the insulation. So you want to try and butt that insulation up to the roof light, and the same kind of idea for the window.
How did the guys on site react to these details?
We got a really good contractor in the end, actually, called DJP, and they'd done a lot of refurbishment. We worked with them before, and they were really engaged and keen to get it right, which is half the battle, really.
I can't imagine it's a huge number of contractors with all of a 20-point detail.
I don't think it's that's not that complicated in my experience. It's more complicated than Kingspan kind of crinkly roof and slap a bit of polycarbonate on it, sure, but this is better. That's threshold and floor and stuff. That window detail. Again, it's we can come back to this if you're interested, but might be better to get into some questions. This is the drainage, and we've got all the drainage basically sits below the floor insulation. We've got a separate floor covering in there, so that insulation just runs straight across the internal manholes that were necessary. So I'll just quickly flick through some photos from the build. So this was the floor going down, so yeah, filling it up with some scalpings to level it off, and then the insulation, so 350 mil in the end in there. That's quite a lot. That's the first piece of edge insulation going in to make sure that connected with the wall insulation above it to minimise the thermal bridge there. That's our wood fibre insulation arriving. That's a bit of local patching up of the wall with block work. We had to get a bit hands-on and do a bit of origami to work out how to so this material here is a membrane that was used for the air tightness. So that's actually relatively vapor open. Again, that's to do with the moisture management. But this was us working out how to form the detail at the end of the internal floor to wall junction. So again, going back to that idea of the 20Ps and the 5Ps, you can't get away with any leaks. So we came up with this idea of having a sort of skirt that went in before everything else to make sure that the air barrier was completely continuous around that awkward 3D detail. So this is the wood fibre boards. That's the rigid one. That's called Passivhaus. And that's the more flexible one for between the frame. That one's called Passivhaus. This is the stuff going on. So this wall's been rendered with a line-based render, and then this stuff's mechanically fixed on with thermally broken fixings. And that's the sort of semi-finished wall before the plasterboard's gone on, and you can see the air barrier in there completely continuous and taped up. That's kind of more of the same. There's a few little bits of steel, none of which penetrated the insulation apart from those thermally broken straps that we talked about. That's a detail of how the window reveal was working. So essentially the Passivhaus triple glazed window sat within that insulation zone, whereas the original would have been out nearer the front of that reveal. So technically, for planning purposes, the building is unfinished because eventually it will have some replica steel frame centre pivot windows in front here, but they're rather expensive. And yeah, we had to have the triple glazed ones for the thermal performance. So on paper the building's not finished, but maybe they'll get around to it one day, maybe not. That's just a shot of the first floor going in. Actually, there's a little bit on the surfaces I want to get onto. This is some of the air tightness detailing. So this bit, for example, is taped. That's a wall-to-floor joint. So that bit of tape went on before the internal wall was framed out, so that we could make sure that bit of membrane was properly taped to the floor. Obviously, if that internal wall had been built before that tape went on, then there would be a bit of a gap beneath the frame there. Builders always put the SVPs too close to the wall, and it's quite difficult to get behind in here to seal that SVPs to the floor. That's one of the original trusses. On one of the other original beams, there was this crack that we had to actually just box around in the end. So that was just effectively covered in a ply box that was taped back to beyond the split. Similar thing happened here where we've got this, where they'd converted it into theatre, this had been notched out to give some head height over stairwell. And there's some horrible bolts in there for a strengthening piece that were just boxed around. That's the window going in. Really quick bit on the services. As I said, it's got to be mechanical ventilation with heat recovery. That was quite tricky. It's quite constrained kind of space. In terms of space heating, the space and hot water heating is just done by this direct fired gas heater. And because the space heating is so low, we've basically just got a plate heat exchanger, which is this one here, which just robs a bit of robs a bit of heat from the domestic hot water cylinder. I think I worked out it was about, because it's youth, it's a fairly high hot water demand. I can't remember exactly what the numbers were, but yeah, it's a pretty small fraction of that heat generated by that bit of kit actually went into the space heating. That's kind of it really. It's a bit of a whistle-stop tour.